The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Now we're going to take a look at example multiple vector addition. Wonderful. So as you swipe at a common housefly sitting on your desk, it travels north for 0.5 seconds. Then as you swipe at it again, the fly travels east for 0.3 seconds, at which point the fly once again changes its path to travel 45 degrees southwest for 0.2 seconds to sit on top of the lamp on your desk. What is the total displacement of the fly from its initial position to the lamp? Wonderful. To find total displacement, again, what we can do is, let's first draw out the path, actually. Let's just highlight all the directionalities that are going to be taking place. North for 0.5 seconds, east for 0.3 seconds, 45 degrees southwest for 0.2 seconds. Okay, so first we'll go north here, right? And that'll be our first change in displacement there. And then we'll go east here, right? Then our third displacement here is going to be 45 degrees southwest for 0.2 seconds, giving us the following, right? As we see here. Wonderful. Thus, our total displacement from our initial position, again, let's please forgive the artistry and we'll imagine these lines are straight, right? Well, this here will give us our total displacement. Great. Let me actually just rewrite that a little cleaner. Maybe if I just use a thinner pencil. Okay, great. That's going to be our final displacement there. And how can we solve this? Well, we can just use our Pythagorean Theorem, right, to figure that out. And we're also going to need to find angle theta here for directionality after as well. Wonderful. For now, though, let's just go ahead and find the magnitude here of our total displacement first. Then we'll worry about angle theta here. All right, great. How are we going to find the magnitude? Well, once again, what we can do is we can first take the vector sum of all three, the x components of all three of the travel points that we have here, right? And then what we can do is we could take the vector sum of the y components of all the displacements as well, right? And then that's going to give us the x component and the y component for the total displacement vector, right? So what we'll do is, on our next slide, we'll break R1, R2, R3 into its x and y components, add them up to get our two values here, right? To get our x and y components for our vector. And with the Pythagorean theorem, then we can go ahead and find out what the magnitude is right here. Now, once we find out what the magnitude is there, from there, we're also going to know the opposite side and the adjacent side, and then we can use the inverse trig function, right, to find out what the direction is, right, or our angle. Now, it wouldn't be a bad idea if you actually pause the video and try it yourself, because we've done a few problems like this. Otherwise, let's just follow along and we'll get through this together. Wonderful. Let's now move to our next slide. Great. So we'll begin here with the x component, right? Well, the first x, well, let's go ahead and just highlight this as well. This is going to go north, this is going to go east, and 45 degrees southwest. The x component for our first displacement, if we go back, well, there's displacement in the y direction, right? So x is just going to be 0. Wonderful. Now, another important point that I should have mentioned earlier, it's telling us here that the average velocity is 1.50 meters per second for the fly. Great. So for our y component here, right, we know that the total time that it is going to be traveling is going to be 0.5 seconds, right? Now, to find the actual displacement for the y component, we have to multiply that by the average velocity, right? And the average velocity is going to be 1.5 meters per second. And once we go ahead and we equate that, we get a value of 0.5 meters in the y direction. Now, let's do the same thing for the second and the third vector and break it down into its components. Now, the component for the second vector, we see it's going to be flying east for 0.3 seconds, right? And the average velocity, as we know, is 1.50 meters per second, right? That's going to give us a value of 0.45 meters. Now, how about the y component here? There is no y component, right? It's just the x component. So let's go back, and for the y component, we can just put 0. Great. Now, what about our third vector here, right? Well, this time, if we go back, we have to account for our, we're going to have to, for our third vector here, when we break it down into its components, we are going to have to account for the southwest angle firstly, right? And as we've been doing all lecture long, west will designate negative, right? So west will designate negative, and south will also designate negative as well to demonstrate that. Wonderful. So what that's going to look like is the negative for the west, right? And then our speed here is, average speed is going to be 1.5 meters per second, but we can also write that as 1.5 meters per second cosine 45 degrees, right? There we go. And our time of travel is going to be 0.200 seconds, as we see here. Wonderful. And then once we go ahead and we equate this, we end up getting a value of 0.212 meters, negative 0.212 meters. Wonderful. Now, how about the y? The y component is going to be negative as well. The negative there is to demonstrate the fact that we're heading in the south direction. Now, that's just going to be sine 45 degrees, right? 0.2 seconds is the flight time. That's also going to give us negative 0.212 meters. Wonderful. Now that we have all our x components and y components, let's go ahead and find the vector sums, right? And we'll start here first for the x component, right? And that's just, as we said, the x component from our first, second, and third vectors here. Perfect. And the value for the first one, I believe, was just 0. For the second one here, it was 0.45 meters that we had found. And then for the last one, we had found that it was actually negative 0.212 meters, right? Thus, when we actually go ahead and we add that up, we'll get a value of 0.238 meters. Now, let's also find the vector sum of the y components. And the vector sum for the y components, right, is going to be just our 3y components, right? And they were just 0.75 meters, right, plus 0. Oh, this M didn't come out well here. And lastly, I believe we had here negative, right, 0.212 meters, right? And that gave us a value of 0.5 0.38 meters. So there we are. We have now our x and y components of our vector. Now, if we go back to our chart, our plot here, so we have this component and we have this component. So we have this component right here, the y component, right? And we also have this component here, the x component. Now that we have the y and the x component of our vector, we can just use the Pythagorean Theorem, right? Because this is a 90-degree triangle, right? To find the length of this side, and that's exactly what we're going to do. And so what are we doing now? We're just going to find the magnitude and direction of displacement. If we recall, our Pythagorean theorem is just going to be the magnitude of the vector squared plus or equals to the magnitude of the x and y squared of the x and y components. Wonderful. Now, once we go ahead and we do the mathematics behind this, recall that the x direction here was 0.238 meters squared plus 0.538 meters squared, I believe. Okay, now once we go ahead and we equate this, we will get a value of 0.588 meters. Wonderful. Thus, the magnitude, right, the magnitude of the displacement is going to be 0.588 meters. Well, let's also find the direction that that magnitude is going to be traveling in, right? And we can do that through our inverse tan function as we have been doing, right? As we see here, we're going to use the opposite side over the adjacent side. And if we just go back to our slide here, the angle there is going to be tan, inverse of tan over opposite over adjacent side. And what is our opposite side? Well, our opposite side is just the y component, right? And that comes out to being, if we see up here, that was 0.538, right? And this is going to be 0.238. That was our x component. And then once we go ahead and we equate that, that's going to be 66 degrees. Now, if we look at the position vector, right, it's actually going to be east 66 degrees pointing north, right? Let's go ahead and take a look at that, right? Because we see here that it's going to be, let me actually just go ahead and write this value in first. So theta is equal to 66 degrees, right? Just to remind us, so as we see here, it's east pointing 66 degrees north, and that's going to be 0.588. That there is our total displacement.